chapter 4, 4.1, we're going to take a look at antiderivatives. All right, so we've looked at something called derivatives before. So antiderivatives, it's one of those prefix words. Anti usually means the opposite of. So this is the opposite of doing derivatives. Now, before we get started with that, what I want you to do is I want you to write down the derivative rules that you know. So if you have these, I think I have 6 of them, 5 of them up here. I have 5 of them up here. These 5 functions, I would like for you to remember real quickly, write down what's the derivative of that. Okay, so fill that in for us first. After you get those 5, the trig ones are on the next slide. And that fills out your first sheet. Mm-hmm. Those of you who are writing things down, do you have all these 5 written down? Let me get these other ones in here too. Okay, if you're not quite done, it's okay. We'll fill the rest of them in together. Let's make sure that we're all on the same page. What did we get for the derivative of the constant y equal b?
Y equals 0.
Yes, and so we'll call it y prime as a reminder. So this is y prime equals 0. What is the derivative of a linear function, ax plus b?
A.
Just a, right? How about when I have a constant multiplier, k times f of x?
It would be k times f of the derivative of f of x.
Yes, the derivative of f of x. So we take the derivative of the function piece and we just multiply by the coefficient that's in front. What happens when I have a sum or a difference?
Y equals f prime x plus or minus g prime x.
Right, we just take each of the pieces' derivatives individually. We liked that one. It's not like quotients and products, right? But it's a little straightforward. And how about the power rule?
Nx to n minus 1.
Okay. Is that good for everybody? We've been doing these for over a month now, probably 6 or 8 weeks at this point, so I think they're okay. The trig rules are the ones that are less maybe comfortable for us because they don't have quite the repetition. We don't use them quite as frequently. But what's the derivative of sine?
Cosine.
It's cosine. How about the derivative of cosine?
Negative sign.
Negative sign, and we like those really well. They just go back and forth, positives and negatives aside, right? How about tangent?
Secant squared.
Ooh, good. Secant squared. And we're writing the angle every time, right? We're not just writing the name of the function. We got the x's in there. How about the derivative of secant?
Secant tangent.
Yeah, secant x tangent x. Cotangent?
Negative cosecant squared.
Yep, negative cosecant squared. Whoops, whoops, whoops. There we go. And cosecant.
Negative cosecant cotangent.
And one of the things that we did as we were learning this is we noticed things like these sort of come in these pairs, right? So we kind of are noticing that like these two pair up very nicely and kind of mimic what these two are doing. We talked about the fact that co-functions always have a derivative that's negative, so cosine becomes a negative sine, cotangent becomes negative cosecant squared, and cosecant becomes negative cosecant cotangent, right? All those kind of things. All right, so here's what we're going to be doing in this chapter. All this chapter mixed throughout, but this lesson specifically today. Instead of starting what we did on the left-hand side and moving to the right-hand side of this list, we're going to be starting on the right-hand side of this list and moving backwards to the left-hand side of this list. That's what we're doing. We're going backwards. So everything that was, moving to the right, you're taking, like, for example, this is a really good one to talk about, the power rule, right, where the power got smaller, right? Our powers are going to get bigger. Right? Things like that are going to happen, okay? So we're going to take a look at a little bit of notation along the way as well. So it was very nice for us on these, for example, to start with y and to become y prime. Agreed? The problem is that if it doesn't actually start y prime here, I need another notation to show you that I've taken an antiderivative. Okay, now if it started y prime, the notation can just be y. That's fine. But if the notation just says y, I need to do something different. And so what we do is we actually capitalize the name of the function. So it's a lowercase y when I start. It will be a capital Y when I find the antiderivative. So all of these, my capital Y's are terrible, by the way. All of these will start out capital Y. So capital Y is going to equal things. There's something else that happens, but you don't notice it very much happening until we get a couple of lines into this. So over here, look back at your first page. Okay, you're going to compare the first page to the second page as we go. When we have, from the right-hand side of your list, a derivative that's 0, how did we get the derivative that was 0? Where did it come from? A constant, right? So when I have the derivative of something and I'm taking the derivative of 0, I get a constant. Make sense? Now here's where it gets trickier. How do I get a constant k as a derivative? What did that come from?
From like a linear function.
It came from a linear function. So it came from a function where that k was multiplied by x. Again, look back at the second one we did. That's how we got a. But there's something else. It might have something else on the end, right? We had ax plus b, and the b just went away. And in fact, that could happen anywhere. Because anytime I take the derivative of a constant, it becomes 0. So when I take an antiderivative, I have to recognize that every single one of these might have a constant on it. It might have, and we put plus c on the end. So there's going to be a plus c on the end of every single antiderivative we write, because it might have a constant that went away if I were going back the other direction, the way we'd gone before. Okay? So when you get to your gateway, a lot of times I'll have people put plus c really big on the top of their gateway to remind themselves, because if the plus c is not on your problem, I'm going to count it wrong. I had a guy once, this has been a number of years ago, and he got every single question right, except he missed plus c on every single problem. And so obviously he knew what he was doing, but he forgot something, and he had to come in and retake it for me. And he was bummed, right? He was bummed he didn't get the extra credit. So we don't want to miss the plus c's. All right, so a constant multiplier. So when we took a derivative with a constant multiplier, the constant multiplier just comes along for the ride, right? Well, the same thing happens here. I still have that constant multiplier. But what will the lowercase f of x become? Capital, right? I'm taking the antiderivative of that piece, whatever it is. So coefficients in front operate the same way. And I have my plus c on the end. And when I have sums and differences, they also operate the same way. I just take the antiderivative of each piece individually, just like I would have taken the derivative of each piece individually. So I have capital F of x. I have plus or minus, right? Yeah, plus or minus capital G of x. And then I still have that plus c on the end. All right, so here's the most interesting one. All of these so far are just sort of like, they're quaint. They're kind of simple and whatever. This is the most interesting. Okay, think about what happens with the power n when you take a derivative. Okay, the power, the exponent becomes smaller by 1. So since I'm doing the antiderivative and I want to do the opposite, what do you think is going to happen to my exponent?
It will increase by 1.
Bigger by 1. It will increase by 1, yeah. Okay, that's not all of it, but this will be x to the n plus 1. Secondly, that n, right, when I take the derivative, comes down to the front as a multiplication, right? It becomes multiplied. So what's going to happen here? You're right, Levi.
Oh, okay.
It's going to be a fraction. Instead of multiplying by n, I'm going to divide. But I'm not dividing by n plus 1. Yeah. So it's divided by n plus 1. Okay, so everything's just slightly different, like alternative universe kind of stuff. You're like, wait a minute, that's just a little bit different than it was before, right? So I've divided where previously I had multiplied. I've increased where I'd previously decreased. And at the end, I write plus c. Yes, I do. Okay, now what you're going to notice as we look at this next list, this is a trig list, is that it doesn't actually have, right, sine, cosine, tangent, secant, cosecant, cotangent. It actually has the exact pieces that were on your right-hand side before. Now that might feel a little bit like fuzzy, like, well, okay, what about secant? What's its antiderivative? You didn't write it down, Dr. Hands. I didn't, but we'll get to it later. Okay, it's just not in 4.1. So all of this list is exactly the list that was on the right-hand side, with the exception of what? What do you notice that's slightly different?
The negative signs.
The signs are not there. All these signs are listed as positive to start with, correct? So we have to keep that in mind as we're putting this back together, is those signs have to actually be present properly when I go backwards too. Okay, so as I'm looking at this list, they're all capital Y's, and they're going to all have the plus C's at the end, right? All that's going to be the same as the previous slide. But who had a derivative that was sine? Whose derivative was sine?
Cosine.
Cosine. And if you think about this, though, what's the derivative of cosine? Derivative. It's negative sign, and this said positive, so what do I need to compensate?
Negative.
I need a negative over here now. And legit, that's how I remember to do these every time, is I go back and remember what did I do for derivatives, and then I fix it. I never memorize this list. I never have, and I've been doing calculus for longer than you've been alive, every single one of you, okay? And I've never memorized this list. I always think about my list of derivatives, and I go backwards. Cosine. Whose derivative is cosine?
Sine.
Sine. Sine exactly, or? Yeah, and then plus c, exactly. So my sine is the positive coefficient, right? There's a positive in front of it, or we don't write anything, and I have my plus c. How about secant squared? Whose derivative is secant squared? Tangent. My plus c. Is it positive? Are these both positive when they go together? They are?
Yes.
Yep, they are. How about secant x tangent x?
That would be secant.
That would be secant. Plus my c. Again, do these go in positive pairs? They are.
Yes.
These are both positives when they go together. Yep. All right. Last two. Told you my y's were terrible. Okay. The last two. Whose derivative is cosecant squared?
Cotangent.
It is cotangent. Right, but it's negative. And I have my plus c. And whose derivative is cosecant cotangent?
Negative is cosecant.
Negative and cosecant. So unfortunately, I can't just look at them and say, hey, look at the cos, like I on the last one, right? Like this is cosecant, this is cotangent, they both became negative, but cosine doesn't work that way. Correct? So you have to be a little bit careful to remember which list does that. It's the derivative list that does that. Okay, so the rest of this chapter, or not chapter, this section, this is not true for the chapter. The rest of this section is applying these rules to functions. It's going to be doing exactly what you're going to be doing for me on a gateway with the simplification piece at the end. And you don't have to simplify in a gateway. Okay? So we're going to take all of these rules and we're going to actually use them. All right. So that means I'm going to have a plus D on the end of every single one, right? Okay, y'all going to help me remember that, yeah? I forget it sometimes too, so you guys can help me stay on my toes. 2x. Okay? Oh, there's a notation that I haven't identified yet for you. This notation right here, it's like this tall, skinny s. This is the notation for antiderivative, kind of like my prime is my notation for derivative. This is the notation for antiderivative. You don't need to write it again when you're working on it. You're just going to write the answer afterwards. This is going to equal this. The dx on the end is sort of like the beginning and the end of a parenthesis. Okay, it starts with the script s, it ends with the dx. So you might be like, well, why don't we just use parentheses then, right? Well, I need the script s to tell me I'm doing antiderivatives. The dx actually tells me what the derivative, what the variable is that I'm doing the antiderivative for. So if our functions had had s's in them, it would say ds on the end. If it had t's in it, it would say dt on the end. And you might still be thinking like, yeah, but why? And the real reason for the why is because when you get to Calc 4, and I know that you're not all getting to Calc 4, but this is where this is leading, and this is why the notation is what it is. There are functions that have multiple variables in them. It might have x's and y's in it. And you need to know what the variable is that you're taking the antiderivative using. Am I using x as my variable in this one I'm doing it, or am I using y as my variable? That's why that notation there is on the end, is because it sets things up to be able to be used fluidly if you continue on into further branches of calculus. Okay, so that's why it's there. So the script s and the dx are either both present or both absent. You never have just one piece. It might help you to remember, too, that when you remove the dx, you put a plus c. Also a red flag to remind you, okay? Okay, 2x. What is the derivative? What is the value for whose derivative? Who gives you a derivative of 2x? X squared, yeah. So this is x squared. Another way you can think about this is you can think about the fact that you're sort of pulling the 2 back up. Right? The 2 is sort of coming back up into the exponent. If you were taking the derivative, it would have come down. So this is x squared. How about negative 3x squared?
It'd be x cubed, right?
It would be. It's negative x cubed. Now, you can think about it again like you're pulling the 3 back up. That's fine. You could also think of it like this. I have a 3, and I have an x. The power is 2. I increase the power. The new power will be a 3. I missed something on the first one. And then I need to divide by the new power 3. I could do the same thing. I didn't miss it, but I could do the same thing on the first one. The power on x is a 1. I increase the power to a 2, and I divide by 2. Okay, so no matter what the exponent or the coefficient is in front, it can stay there. You can increase the power by 1, and then you can divide by your new power. Obviously, on this one, if I were simplifying at this point, or if I had recognized it as I went, this is just x squared minus x cubed. And I also need a plus c. So on your gateway, you are actually welcome to leave it at that first line if you'd like, if you're doing it sort of like piece by piece like that. But when we get to our homeworks and as we work on things that were on quizzes or tests, you'd clean that up a little bit. Simplify any coefficients and divisors that you have. Okay, number 2 has something in the denominator. You might notice we didn't have anything that told us about what to do with things in the denominator. So the thing is, we're going to need to rewrite that to look like things we can do. How can I rewrite 1 over x to the 6th to be able to use the properties I have? Yeah, x to the negative 6th. So we'll start with that. What do I do with the negative 6? I plus 1. So what's negative 6 plus 1? Negative 5. So this is x to the negative 5. And then what do I need to do with that piece? Yeah, divide by the negative 5. So the exponent and the divisor will always match when you're doing this. How about the 2? What do I have to do with the 2? Yeah, I have to multiply by an x, right? I have to include the x next to it. So I have negative 2, and then I'm including the x now. And then what do I need? Plus c. So again, this is where I would stop for a gateway. But when we're doing things otherwise, if the problem started out with x to the 6th in the denominator, the problem needs to end with our x to the 5 in the denominator. So the simplification step that I will be doing would be that I would have 1 over negative 5x to the 5th minus my 2x plus my c. Sure. You absolutely don't have to put the negative with the 5 at the bottom. It could be at the very front. It could even be on the top with the 1 if you want. Doesn't matter. Are these okay so far? Okay. Bit messier. Get messier as we go, right? I have an x and I have a square root of x, and they're both in the denominator. Let's deal with the square root of x part first. How can I rewrite square roots so that I can use the properties that I have? Yeah, it's a power of 1/2. So right now, oops, it didn't switch screens. Yeah, it is significantly messier. Okay, so we had mentioned that this piece right here in the denominator is at x to the 1/2. What is the exponent on the first x? It's a 1. So what I really have in the denominator is a 1.5 exponent, right? 1.5 is not very friendly to work with. The improper version of it is a little bit easier to work with. So what's the improper version of 1.5?
3/2.
Yeah. This is 1.5. This is the same as 3/2. But it's 3/2 in the denominator. I want it in the denominator. So I'll pull it up, just like we did on the previous one, and make it a negative 3/2. Okay, so rewriting is really important for your first step. Good with the rewriting? Okay, so what do I do for a power rule with a negative 3/2 x to the negative 3/2? I plus 1. So what do I get when I take negative 3/2 and I add 1? I do. I get negative 1/2. And then what do I do? Close.
Negative 1/2.
Yeah, divide by negative 1/2. Here's my plus c, and on a gateway, you're done right there, and we all say, whew, that would be a great place to stop. I don't want to do anything else. But for your homework, right, for quizzes, for your tests, you're going to simplify that, and it's going to look like the original problem. So no negative exponents and no fractional exponents, because the original problem didn't have them. So what do I have to do? And also we got division by a fraction. That's just tacky, right? It's just not good at all. So let's deal with the negative exponent part first. What do I do about the fact that I have a negative fractional exponent? Move it to the bottom. That'll make it positive. And I put it underneath a square root. Yeah, cool. Okay, so this is the same thing as having square root of x on bottom. Now what about the fact that I've divided by negative 1/2? Yeah, you multiply by the reciprocal, right? Division by a fraction is the same as multiplying by the reciprocal. The reciprocal of negative 1/2 is negative 2. So it's just negative 2 on top. I think I've said this before, but I'll say it again. It has been said people don't get good at algebra until they take calculus. Do you believe it? It's true for me. All right, next one. You might have noticed I didn't tell you anything about product rules, right? There's a very good reason for that. There's absolutely no product rule that exists for antiderivatives. That's both good and bad. It's bad in the sense that it means we can't use it here. If it existed, we could use it, right? It's good in the sense that means that we must be able then to change things and to do them without having an additional rule, right? The also reason that it's bad is that means that for calculus questions that are much more complicated than we're going to do this semester, like things that show up in Calc 2, you need a variety of other measures about how to deal with those. And so there's a whole chapter on what you do when things look like products and quotients. And there's no simple answer. There's just a bunch of optional possibilities of things that might work. Okay? For this one, though, what could we do to this to make it workable? Multiply it out and use our algebra skills that we talked about, right? Cool. All right, so if we multiply this out, we're going to get 3x squared. Let's see, this is 3x and this is negative 2x, so that's positive x. And then at the end, I have negative 2. It's not a hard multiplication step. And at that point, it looks like the very first one that we did. and a little bit of the second one. What's the antiderivative of 3x squared? It's x cubed. Or feel free to write 3x cubed over 3. It's x cubed. What's the antiderivative of x?
1/2 x squared.
Okay, so it's x squared, and then it's divided by 2, or you could write it as 1/2, like Josh said. Right? You add 1 to the power. The x has a power of 1. That's why it becomes a 2. What about the negative 2?
2x.
Yep, negative 2x. Thank you. Plus c. dx goes away, the plus c comes in, right? Okay, I'm going to do one more. One trig problem, and then I think that we will pause and we'll pick up next time with the rest of it. So you won't have homework due on Wednesday. We'll wait until Friday because there's too much of the lesson left that I want to do with you. I don't want you to just watch a video, okay? That happens after tests sometimes when we talk about tests. So it's all right. Cosecant x, cotangent x. We got trig involved. What about the 1 at the beginning? Let's start with that. What's the antiderivative of 1? 1x or just x? Either way, yes. What's the antiderivative of cosecant x, cotangent x? It's negative cosecant x, but there's already a negative here, right? So I'm going to put the negative here. And then I'm going to write the negative cosecant x. And if you see that and you just want to write it as plus to start with, that's totally fine. This then is a plus c. And if you didn't already do so, you would simplify it by writing it as x plus cosecant of x. Okay, so we're going to push pause there today. We will pick up on number 6 next time, finish this lesson, and move on to 4.2.